Okay. I'm very happy to see the turnout that we have online and in person for Jake's lecture. I'm glad to see as many people are as interested in this topic and Jake, and they're excited to hear him speak as I am. With that being said, it's my pleasure to introduce you to Dr. Jake Turner, who is the NASA Hubble and Carl Sagan postdoc fellow at Cornell at the Carl Sagan Institute. Jake received his bachelor degree in physics and astronomy in 2011 from Arizona. As a grad student, Jake was awarded a National Science Foundation Graduate Research Fellowship and spent 2 years as a visiting student at CNRS in Orléans, France. Dr. Turner received his PhD in astronomy in 2018 from the University of Virginia. Since 2018, Jake's been a postdoc researcher at Cornell, and he's been awarded the NASA Hubble Fellowship in 2021. Jake's research is focused on studying the magnetic fields, atmospheres, and orbital evolution of exoplanets. In addition to his research, Jake is very active in social activism, photography, outreach, and he also runs the social media of the Carl Sagan Institute. And with that being said, it's my pleasure to hand things over to our guest lecturer, Dr. Jake Turner.
All right, thank you very much. Am I allowed to put my mask off?
Yes.
All right, thank you everyone online and in person for being here. So today I'm going to be talking about our search for LEGO mission from exoplanets using LOFAR beamformed observations. So I'm just going to jump right in. This works? Okay. So I want to start by acknowledging all the main collaborators on this project. So the main results I'm going to be talking about has already been published in this paper that you can see on the screen. I want to acknowledge my collaborators Philip Zarka, Sean Mateus Grasmeyer, and Robert E. Johnson, the main people who worked on this paper, as well as the other people on it. So I just want to start with that, as well as all the funding agencies that you see here that have helped with this over time. Thank you very much. So this is going to be a very, very, very brief summary of exoplanet research. So there's thousands and thousands of exoplanets known, approximately 5,000. There's tens of thousands of candidates that we know. This is every day there's new planets being discovered. So this is a very fast-moving field. People are studying their fundamental properties, their mass, their radius, orbital distances, temperatures, all the time. Orbital variations and atmospheric characterization is one of the fastest moving fields, especially with the upcoming James Webb in the next few months and 2 years. So it's a very fast moving field. There's a lot of things going on. So, but you might ask, what about their magnetic fields? This is where I come in. So I always like this quote: the larger one's ignorance, the stronger the magnetic field. It seems like magnetic fields are very difficult and get in the way of a lot of things. So let's just take a step back. So what about our solar system? So we know from our solar system that all the planets, except for Venus, had or has had a magnetic field sometime in their history. Also, the moon Ganymede has a magnetic field. And I show a figure here of some of the dynamos for some of the solar system planets. They're quite complex. They're not all the same. The tilts are different. It's a very complex field. So it's very ongoing, especially like with Juno, everything with Jupiter and stuff like that. So for a very long time, people have expected that there should be magnetic fields on exoplanets, both from comparing our solar system and looking at brown dwarfs and also stars. And the search has been ongoing for many, many decades. So far, we haven't had a definite detection. So why should we even care, right? Because a lot of people don't even really talk about magnetic fields, especially in exoplanets. So the first thing you can learn is if you detect a magnetic field in an exoplanet, you can start learning something about the interior structure of the planet, because the interior structure creates the dynamo in the first place. So for Jupiter, that's metallic hydrogen. For Earth, that's iron, for example. And for exoplanets right now, we know a lot about their masses and radii, but there's a lot of degeneracies that if those are the only two things you know. And so having an external constraint such as a magnetic field will help understand what is going on in the interior of these planets that are thousands of light years away, which also relates very much to how they formed and how they evolved. Another thing that people talk about a lot is atmospheric escape. So we think that a magnetic field might be one of the components that contributes to atmospheric escape and evolution. And this is a figure from one of them, from MAVEN, that shows that this might be an important process in our solar system. This is very highly debated though, so there's still lots of work to be done on that part. There's also a really interesting thing from the Kepler mission. I show here on the left, the planet size versus the number of planets detected. And you can see that there's a planet valley that people call the Fulton Gap, stuff like that. So there's a distribution of hot, close in super Earths and farther out of Neptunes, and something in the middle. And so people have a lot of thoughts of why this could be the case. One reason could be the magnetic field differences of the planets. That's still up for debate as well. Also, there's been a lot of work to see if some of these ultra-hot Jupiters and hot Jupiters, if they have a magnetic field, does it actually change the atmospheric dynamics and evolution of the planet? Some studies have shown it does. It changes like hot spots, atmospheric distribution, like stuff like that. So it's kind of interesting to think about. And then everyone's favorite, habitability. So I always like this plot, very complex. It's from the Meadows and Barnes review paper. And they tried to kind of get the consensus of what are all the things that we think go into having a planet be habitable. There's a lot of things on this, as you can see, both from the atmosphere, the star, the planetary system, the surface. There's a lot of things that go into this. And one of the things that they think that does go into this, possibly the magnetic field of the planet. So it might be important, it might not. We're not quite sure, but it's definitely something to take into account. Also, if you care about exomoons, this is everyone's favorite, some people's favorite topic to think about are their moons and around other planets. So you might be able to detect exomoons using radio observations of the magnetic field. Also, star-planet interactions has been in the news recently. So if your planet, your hot Jupiter, is really close to its star, it might actually be able to magnetically interact with its star and actually change the star itself in terms of star spots and other magnetic activity. So if you care about stars, you might also care about this as well. So hopefully I convinced you that there are many reasons why you should care about magnetic fields, besides the fact that they're cool and really interesting. But there's been a lot of techniques that people have thought about over the years and continuously publish about this, of how you can actually detect them. Unfortunately, though, there's a lot of false positives for these techniques. And there was a review paper by Grexmeyer, one of my PhD advisors, 2015, that reviewed all of these techniques and tried to see if there was false positives, false negatives, et cetera, And one of the best techniques they found that had the least amount of false positives is radio observation. And that's what I'll be talking about mostly today. And all the other techniques have a lot of false positives. I actually worked on some of those in my PhD for like with bow shocks and stuff like that. So going into that, so just jumping right into actually what we're observing when we talk about radio emission from exoplanets. So what we're actually observing is electron cyclotron emissions. So let me try to see if this plays. So in our solar system, the stellar wind comes from the star, from our sun, and it gets caught in the magnetic field of the planet. And those electrons and protons and stuff gyrate around the magnetic field lines and actually create a radio emission. And in this video, the same, it's kind of showing you the same emission that creates the radio eventually also creates the optical aurora. So there is some kind of connection there. Next. So this technique has been used in our solar system for a long time. Actually, for all the magnetic planets that have been used. So you've actually we're able to discover this on Jupiter first, and then subsequently, when you have spacecraft in space, you're able to figure out this is happening on all the solar system magnetic planets. So the plot here I show is frequency versus flux, and this is showing basically the radio spectrum for some of the solar system planets. And the most important thing here is the ionosphere cutoff. So anything on this side of the plot, on the left side of the plot, you can only observe from space. Anything on this side of the plot, you can observe from the ground. So the only planet you can actually observe from the ground is Jupiter. And so that's the unfortunate part. So if you're going to be doing this for exoplanets from the ground, you're mostly going to be looking at close-in hot Jupiter planets, brown dwarfs, stuff like that. So if you want to go look at Earth-like planet magnetic fields, you probably have to go to the moon or space, stuff like that. So that's research that a lot of people are looking into as well. So the main thing is that the gyro frequency of the emission is actually directly related to the magnetic field. of a planet. And so if you have the spectrum, you can actually, at the maximum frequency you see tells you what the actual magnetic field of the planet is at the pole. We expect this emission to be 100% circularly polarized, which is really good. So there's not a lot of things in the universe that are circularly polarized. So that helps with interference and also with understanding what your observation is. We do expect this to be beamed from our solar system. This is, you don't always see the emission. So for example, if you just randomly look at Jupiter, only 10% of the time you will see this emission. So there is a beam that sometimes sweeps towards Earth, kind of like a pulsar, if you want to think about it that way, or like a lighthouse. So sometimes it's being towards you, sometimes it's being away from you. And we do expect the flux from the planet to be much greater than that of the star. So this is not a new idea. So as far as I can tell, from doing a literature search, the first time this was ever mentioned was in 1977. This was in a conference, but apparently this paper was never actually published, which I thought was interesting. But this was an abstract from a conference and the search for extrasolar Jovian planets by radio techniques. So this is definitely not a new idea. A lot of people have been thinking about this for a long time. So just going into, can we actually do this from a theoretical standpoint? So this plot is showing what is called the magnetic Bode law. So if you look at either the magnetic power or kinetic power, if you think about it as a pointing flux onto the solar system planets versus their radio power, you see that there is some kind of correlation here. And if you extrapolate that correlation to where we expect hot Jupiters, their radio power is going to be much greater than what we see in our solar system. It could be up 10 to the 3, 10 to the 5 times greater than that. But the interesting thing about this magnetic Bode law is it actually did predict what we successfully saw at Uranus and Neptune. So it actually already predicted something that we've seen. So does it work for hot Jupiters? That's what we're trying to figure out currently. And there's a lot of research that goes into it in terms of like, can you actually extrapolate it that many orders of magnitude? There's also some thoughts that if you go beyond even hot Jupiters in terms of stars, this might actually hold as well. So there's a lot of research that goes into it. But then you also want to predict what are the magnetic fields of the planets themselves. So there's a lot of uncertainty in doing that. So you have a limited number of solar system planets. You can figure out what kind of scaling laws you can apply to exoplanets. And this is just a review paper showing some of those scaling laws that exist in the literature that fit our solar system pretty well. And I always approach this being agnostic and saying that observations of more planets, exoplanets, and now if you have tens to hundreds of thousands of exoplanets, we can actually get some more constraints on these scaling laws. And this is showing one example here on the left, which is on the x-axis is heat flux and magnetic field, and it shows kind of the solar system planets and some stars, and there's kind of some kind of power law you can think about. Whether this fits or not is another story, but the hot Jupiter should lie somewhere in the middle of there. I think so, maybe like about Jupiter's magnetic field or maybe greater. So that's what we expect from theory. So if you kind of combine those two things together, you kind of get a plot like this. This is a very interesting plot. So on the x-axis, you have the frequency observed at Earth. So you think about this magnetic field of the planet itself versus flux density that you observe at Earth. So this includes the scaling law plus like attenuation from how far the planet is away. All these triangles show known exoplanets at the time this plot was created, Regressmeyer 2017, and these are their predictions. And then they overplot these versus telescopes that are on the ground or in space. For example, you can take the lunar array prediction that hasn't been built yet. And your hope is that the sensitivity curves that you see, if there are any planets above that, those might be good candidates to look at, right? It's a good roadmap. So if your planet is orders of magnitude below, maybe you should look at it. If it's around the sensitivity curve, within a factor of 2 to 5, maybe it's good to observe. And so you can see there are planets that are above, for example, LOFAR. If you have a lunar array, there's actually a bunch of planets you can look at. SKA low, there's even more, and that's built in the next 10 years. So this gives us hope that there might be some candidates to look at. So as I said, I was not the first person to do this. This is a non-complete list of all the people who've tried to do this with a variety of different telescopes. I just like showing it because I'm not the first person to do these observations or even think about this. And almost every radio telescope that has been built, people have tried doing this, either blindly, just looking out into space, or looking at stars, or looking at when we finally knew there was exoplanets around them, doing targeted searches. So there's a variety of techniques, variety of telescopes that people have done on this. So I just wanted to show this because it's showing that I'm not the first person to think about this, and not the first person to actually observe. So the telescope that we use is called LOFAR. It's a radio telescope in the Netherlands. So we're actually using the core stations. You can see that on the left. It's actually, the core stations are actually on an island, many kilometers across. And there's actually two different types of telescopes. You have the low band and the high band. We use the low band. The low band are all these little dots that you can see in the island. The high band are more like the tiles. And then if you see a ground view, you can actually see all the antennas that we have on the ground. So they're basically a bunch of dipoles that we phase together to try to look for these very faint signals in space. So I started as an optical astronomer, so it's always very interesting to see that this is a telescope. It's something you can study the universe with. So it's just always interesting to see. So the setup that we do is we're using beamformed observations. So basically we create a digital beam on our targets. If you think, one might think about this like a pixel on your target. And then we have two off beams that are in empty sky, and we use this to basically calibrate the on beam. So if there's any variation from the instrument itself or the sky, the ionosphere of Earth, we're hoping those off beams can be used to subtract those out, as well as monitoring like radio frequency interference from humans and stuff like that. So that's the hope of this kind of study. And we observe from 16 to 73 megahertz. It's almost as far as you can go from the ground. We use all polarizations, so basically SOAP D, that's one I'm going to talk about today. We have very high time and frequency resolution. We don't actually think this will be useful for exoplanets because we're probably going to have to bin a lot of the data together. But this is very useful for getting rid of that contribution from humans, radio frequency interference. Humans love using radio to communicate. So we didn't make sure that we get rid of this as good as possible. And we expect to have pretty good sensitivity from our telescope. So going back into the targets that we looked at for this study was Tau Bootis, Upsilon Andromedae, and 55 CNC. And all these targets basically lie above the sensitivity curve of LOFAR. So this is, as you can see, there's like maybe 5 targets. We looked at 3 of those. So we're trying to see if these predictions are correct in any way. So we asked for time to observe the entire orbits of these planets. Unfortunately, they did not give us time to do that. So because we were trying to maximize the uncertainty that if sometimes the beam will be pointing towards us or away from us. So for Tau Bootis, they gave us 20 hours of observations. That's unfortunately only 25% of its orbit. Upsilon Andromeda B, they gave us 45 hours. That's only, again, 40%. But for the inner planet of the 55 CNC system, 55 CNCE, they actually did give us 100% of the orbit. So that was nice, and you can see that plot there. So I'm showing here basically the orbital phase versus when we actually observed. And we were trying to observe in terms of the year or day of the year of the planet, so to speak, all at the same time as much as possible to limit any variability from the star that might have caused. So this is kind of showing, because I worked on the pipeline for this during my PhD, and I always say this is like, many years of work in one slide kind of thing. So I'm actually showing some real data that we took for LOFAR here. It's a very small snapshot of the data. You can see it's about 40 seconds of data. It kind of just shows you kind of like what's going on. So you can see the raw data. There's a lot of stuff going on. There's a lot of things going on in this data. But if you look at it in terms of the time series, so you can get over all frequencies or overall time, you kind of see some things pop out. So the first thing you see pop out are all these nice spikes. You see that? It's pretty obvious, at least on this observation. And that's basically radio frequency interference. That's interference from humans. So we got to get rid of that. And then also the telescope is peaked, and the gain of the telescope is peaked between 50 and 60. So we got to get rid of that response as well. And so just kind of going into you know, we have several papers that discuss the pipeline in way too much detail for a talk, but basically we kind of show some of the results here of it's like 40-second slice. So you can see that basically all of the large radio frequency interference that we see is actually gone. And then this response of the telescope has been corrected for as well. So now we can actually look for stuff across the entire spectral range. And it more or less looks like random noise. So our pipeline is working really well, so we're going to start searching for this. So how do we search for this emission? So we wrote a paper validating our search ideas on Jupiter. So we actually took an observation of Jupiter. So this actually shows an observation of Jupiter's dynamic spectrum, time versus frequency, and you can see the flux. You can see there's a lot of features here in terms of what the actual spectrum of Jupiter looks like. People study this for their entire PhDs and stuff like that. There's a lot of details that go into why there's this structure. For exoplanets, we might not be able ever to see this kind of structure. So we kind of just want to like dilute the spectrum as if it was an exoplanet. So what we did in this study is we took the spectrum and then we scaled it as if it was a hot Jupiter. So you can't see pretty much most of the structure anymore when you do that. And then you put it like in the noise of your data, you see if you can recover it and like at what stage of sensitivity can you recover it and how do you actually recover something versus like slow emission versus burst emission. So it gave us a way to think about how to search through the data. So the first way you can think about is like slow emission. So I'm showing here now the Jupiter beam versus the off beam. So this is now showing like an integrated spectrum, either an integrated spectrum or a time series. Like again, this is integrated over all frequencies. So on the left, you can see you have time versus flux. And you compare the Jupiter beam, which is basically our on beam, with Jupiter added as if it was an exoplanet. So it's like very, very much scaled down. And you can see there are some variations there that look like there is flux. So we can say that like during the beginning and the end of this observation, there might have been some flux from this scaled up hot Jupiter from Jupiter's emission. And then you're like, okay, what frequency is that actually observable at? Most of it's actually coming from a certain frequency range. Again, this is not actually the real frequency range of Jupiter, but this is where we put it into our data. So you're like, okay, this is coming from a certain frequency range. So that's one way, it's like the most obvious way, like just look for it within frequency and time. And then a less obvious way to look for burst emission is if you actually high-pass filter your dynamic spectrum, get rid of any variations that are longer than like either seconds or minutes, you can actually start to look for spikes, basically, in your emission. And then sum up different ways to do that. I'm not going to go into that and talk about that a lot in our paper, but you can start looking for different statistics of like how you look for those spikes. Obviously, this one you can kind of see by eye, but you're usually not going to be able to see these by eye. So you have to sum up a lot of these different spikes. So maybe most of these spikes are like less than a signal noise of 1, but if you have thousands of them, it might actually be able to be detectable. So it's kind of, you're kind of like trying to average out the noise. And this is an example of showing our on versus off beam, and you can see there's a lot of emission there. So now actually going into the real data of the actual exoplanets that we looked at. So this is showing some of the reduced dynamic spectrum. That's basically non-detections that we have, but that's kind of like what they look like. So you can kind of see there is some random noise. There's still some systematics either from the ionosphere or the instrument itself. And so we're hoping that actually goes away when we compare it to the off beams. And thankfully it does. So when we look at our observations, most of the way that we looked at our observations were non-detection. So we had thousands and thousands of plots that we looked at. I looked at by eye during my PhD, and I'm hopefully going to develop a way to do that with machine learning eventually, so I don't have to do that all the time. But this shows an example of one of our observations on the left. So it's the time, again, versus flux, and you can see the 3 different beams. You can see there is some variation to the ionosphere of Earth, but when you subtract them out, it's basically random. So our off beams are doing really well. They're actually doing what they're expected to be doing. So pretty much for every observation, when we subtract the 2 off beams from each other, they're the same within random noise. So that's really good. So for all observations, when you subtract the on beam from the off beam, it also looks like random noise. So most of our observations are non-detections, actually. But it's really good. We're actually getting pretty good sensitivity in terms of our instrument. And then this kind of shows, if you overplot a bunch of different integrated spectrum, you can kind of see there's actually some small level systematics that are left over, unfortunately. And you can kind of see there's almost this like sinusoidal pattern here. And that's actually, we think, is due to imperfect phasing of the telescope. So there's still some imperfections even in the engineering of the telescope that people are working on trying to fix. So there was one observation that did show some signal. So on the left, I'm showing again time versus flux, and you can see right away when you compare the two off beams to the on beam, there is some additional flux there. When you compare the two off beams to each other, this brown line, they're basically the same. When you compare either the on beam to either of them, you see that there's some kind of excess flux there. But then if you look at frequency, you can actually see that this flux is coming from a very specific frequency range, basically about 21 to 27, 30-ish megahertz. So you can kind of see that very, very distinctly by eye. See, there's definitely something interesting there. So if you just look at this as the time series, it's about a 6.9 sigma detection. If you look at it with actually the frequency range that it's actually emitting, possibly, it's about 8.6 sigma detection. So from the frequency range, we can get some kind of constraint, assuming this is actually CMI emission, assuming it's from the star or the planet, we can get a constraint of about 11 Gauss, basically. So, it's very interesting. We have an interesting signal that we have. So if you look at this signal now, which we originally didn't think we could actually do this, but we looked at it in the dynamic spectrum range, basically. So now you can see time versus frequency. And if you look at the on beam versus off beam versus the two off beams, you can actually see the emission by eye. We weren't really expecting that. So this actually is a really bright signal compared to what we originally expected, but it does look very interesting. There is definitely some kind of interesting signal there that we're very interested in. So going into the next part is a burst emission. Again, we looked through all of our observations looking for bursts. We did not see anything for most of them. So this is kind of showing what a non-detection looks like in one of these statistics that we created. So the on versus off is kind of like doing what it's supposed to be doing, and the off and off are kind of overlapped. And if you see these dashed lines, the first dashed line is the 1 sigma uncertainty if you run a lot of models, assuming random Gaussian noise. So these are kind of just kind of in that area where we expect random Gaussian noise. So there are two interesting observations. The first one we think might be a real signal. So this is, again, from Tau Bootis, and if you look at the on minus off, you can kind of see there's kind of some signal that actually goes above the two sigma line for random distribution of just random noise, as well as even the 3 sigma line. And if you compare that to the off beam, it's a very distinct curve. It actually is statistically distinct from those two curves. Unfortunately, it's only about a 3.2 sigma detection, so we still need definitely follow-up observations on that one. And it's at a slightly different frequency range than what we detected it for. And then we did see like this very marginal signal from Upsilon Andromedae. That's like a 2 sigma detection that we don't actually think is real. It's just interesting to like talk about it and think about it. So I'm going to skip over that real quick. So we go through the paper a lot of like the arguments of what if it could be a planet, or if it could be a star, or if it can be systematic. And I'm going to go over that very, very briefly right now. So we do expect from our solar system and also modeling that the planetary emission should be much greater than any stellar emission that we see. We also expect that the magnetic Bose law should hold possibly for solar system. It holds for the solar system and also possibly for binary stars. It might hold for exoplanets, it might not. This is definitely an area of research. So for Tau Bootis itself, there's been many external observations from Mars, for example, from photometry and also X-rays that show no stellar flares from the system at all. So stellar flares could be contributing to our signal that we're seeing, but there's been no observations of this in the past. That doesn't mean we didn't observe it now. So we do actually see the circularly polarized. Most stellar emission is not circularly polarized, unless it's a stellar flare. Also, the magnetic field of the star is quite low. It's actually been measured to be quite low. So we actually don't think this is a unipolar inductor, kind of like an Io Jupiter kind of system going on there. But there are arguments that it might not be planetary emission as well. So stellar flares are still possible. We can't discount that. Also, there might be small-scale magnetic structures that we don't see when we actually measure the magnetic field of the star itself. And also, there is an M-dwarf companion star to Tau Bootis that we really don't know much about. So that's still also something interesting. But if we assume that this is coming from the planet, again, this is an assumption. We're still trying to prove this, and we're going to talk about how we will do that in the next few slides. Is basically we get a magnetic field constraint between 5.5 and 11 Gauss, and that's about 9.4 the magnetic moment of Jupiter. And again, this is consistent with theoretical predictions. And so we get different constraints from the burst emission than we do from the slow emission, and so we kind of show kind of those constraints there. And then this plot here is showing kind of the predictions versus where we actually see our observation at. And you can, and number 9 is actually where we see that, and some of these predictions with the yellow curves are what we predicted before. So it kind of goes along with that. So how this connects to why I've been here this past week at APL is I've been working with Reza and Anthony on a paper to just try to do some predictions for all exoplanets, including Tau Bootis, of what we expect. And I think this video should play, hopefully. So Reza has been developing a code to try to get a better prediction on this beaming effect that I was talking about, and whether there are some systems that we know the beam might not ever point towards us versus some systems that they might point towards us. And so this has been a new development in the field in terms of the paper we're working on. And so that's kind of the video kind of showing the planet and some of the angles that we care about there. So stay tuned for this paper, but then this is kind of showing the prediction and where we see Tau Bootis actually matches up pretty well when the beam should point towards us. So this is being applied to more exoplanets, and so stay tuned on that. So the next steps that we're doing is we have a large follow-up campaign to basically search for periodicity and the detected signals. So we're going to try to observe the same phases over again to see if every time the planet is there, it basically emits radio waves. Because if you get some kind of periodicity, it should be coming from the star. Or sorry, it should be coming from the planet. And so we got a variety of telescopes to try to follow that up. And so stay tuned for that. And then we're going to take a next step forward, and we're actually going to be using a new telescope called LOFAR, which is in France. It's actually predicted to be about 10 times more sensitive than LOFAR. And so again, I'm showing some of these sensitivity curves here, and there are now another handful of planets that are above the sensitivity curves of LOFAR. So that's actually the next step as well. We're trying to do this on more planets to see if there's some kind of systematic signal that we see that they're always emitting bursty emission or something like that, or just to actually see more planets, hopefully. So, so that's basically about the research I talked about. I do a lot of other kind of research as well. I want to mention this in case anybody wants to chat offline or while I'm still here at APL. So I do a lot of exoplanet transits, a variety of different telescopes, tests from the ground. I've done near UV transits from the ground as well. I'm currently PI of a large atmospheric program with high resolution observations. I search for orbital decay with tests. I also use other methods to search for magnetic fields, such as bow shocks and spectral polarimetry. And then even in our solar system, I've looked at methane lakes and Huygens in the surface, and I also done occultations on New Horizons and Lucy. So if you have any questions about that, we can talk about that offline, but I just wanted to mention that in case other people have any questions. So this is kind of a summary of everything that I was talking about. So we do have these tentative detections from the Tau Bootis system that could either be coming from the star or the planet. So we're still trying to determine that ourselves. We do see the slowly variable emission also there's a burst emission. There is also some uncertainty that the slowly variable emission might actually be a systematic. So I go on that a lot in our paper. I didn't talk about that today. But there is some systematics that we're still very much worried about, which is why we're trying to do multiple telescopes, so that we see the same signal on different telescopes. it's more likely not as systematic of one telescope. So assuming planetary emission, we get a maximum magnetic field strength of 11 Gauss, which is comparable to Jupiter with the uncertainties that we have, and about 0.94 is the magnetic moment of Jupiter. And we don't see any emission, as I didn't really talk about, from 55 CNC and Upsilon Andromeda. We have some upper limits on these planets, but for 55 CNC, it's a really good constraint because we actually observe the entire orbit. For Upsilon Andromeda, we still need more observations to see if we just missed the emission from the beaming. So we're doing follow-up observations, multi-site simultaneous, to try to follow up these first interesting signals that might be coming from an exoplanet, might not be. We're trying to confirm that. And so I'm also looking forward to working more with people at APL on this research and maybe other research. So thank you very much.
All right. Thank you, everybody. Thank you for attending. It looks like we have a question too on our chat as well. Okay. This question is from Elliot Bonilla. He asked, with our sun going into cycle 25, becoming more active, are there any ongoing calibration efforts for calculating flux density?
Not that I know of, but that's an interesting question. I didn't really think about that. But we have seen from our solar system for many years that when there are stellar storms like on Earth, that we do see the radio emission from Earth varying quite drastically. So that's actually been known for many decades now. So, but now that we have more telescopes and like Juno and other things, I think that might be interesting. But one thing that he might not be thinking about is all these observations we take for exoplanets are at night. That's for several reasons. We don't want any contamination from the sun, which we don't think there should be, but just to make sure. And also most humans are asleep at night as well. So, so that helps with the RFI conditions. Because if you observe during the day, you most likely can't get a single good observation due to the RFI. But also with the sun being more active, we also want to make sure we don't include that in our observation, just to make sure that we're not having any false positives from the sun. But simultaneously, we also don't observe, either we have a beam on Jupiter or we don't observe when Jupiter is above the horizon. So we're trying to take as many precautions of what we know is emitting in our solar system as possible.
Okay. Thank you, Elliot, for that question. Also, if anybody has any questions, feel free to unmute at this point and discuss them freely. One quick question that I have personally was, I know you kind of skimmed over it in one of your slides. Why don't you think the 2 sigma detection from Andromeda was real?
Because we did a blind test where we assumed we didn't know what the on or off beam was. And basically, if you don't assume that, so that was, I believe that was confirmation bias. Because if I did a test where I just chose a off beam and acted like it was an on beam, and we found 2 sigma detections all over the place. So that was just a confirmation bias because I was looking through all these plots versus on versus off, and I said, oh, that looks like an interesting detection. But then when I did it blindly and actually looked at the off beams as if they were on, I also found 2 sigma detections. So that's why I don't think it's real. But it's interesting. And so I think we put it in our paper specifically because if people want to observe the same phase, and so if you observe the same phase again and again, and you see a 2 sigma detection every time, then you're going to actually build up that and get away the uncertainty from that.
I know we've spoken about this before, but I think it's valuable to bring it up for various reasons here. When you're considering your off beams going on simultaneously to your on beams, do you lose any sensitivity because you're creating new beams?
No.
No?
So for LOFAR itself, you have a certain amount of actual processing power. And so you can either put all that processing power into one beam, which means you can get actually higher time and frequency resolution, even like larger frequency coverage as well. So the only thing you lose is like, so we could have observed from 14 to 74, but then we would have not actually had an off beam to compare it to. So, and we realized that we needed 2 off beams to do this because when we did it with 1 off beam, there was some of these like false positive 2 sigma detections that we would assume was real if we didn't have another off beam. So this is something that we did realize. And so some of our new observations, we actually have 3 off beams because we know roughly what frequencies we should be looking at. We only need to observe at 50 megahertz right now because we're trying to follow this interesting signal. So we actually are getting as many off beams as possible. On LOFAR, I think we have 4 to 5 just to make sure there's not any uncertainties that we don't understand, as well as systematic stuff.
Can I ask a kindergartner question?
Yeah, of course.
How do you pick the direction of your
Yeah.
optimal configuration?
So yeah, we also talked about this in our paper. So basically, I have a slide about it. So basically, we need the off beams to be within the station beam. So all the beams I've been talking about right now are actually digitally created. So there is actually a beam that physically the actual instrument can observe in. And within that station beam, you can create as many off and on beams as you want. So we need to make sure that our off beams are within that area, which is about, I think I say here, about 10 degrees. So it's actually quite large, right? So it is a large area. So we also need to make sure that it's far enough that it actually, the on beam doesn't overlap with the off beams, and also that any of the side lobes don't overlap as well. So there's definitely a play you have to do there. So that's about 13 degrees as well. And then you also want to make sure that your beams are within the same, what is called an exoplanetary patch. I don't know if you've ever heard the term before, but it's basically the size of the atmosphere that we are assuming is behaving the same. I learned about this when I was doing like optical astronomy, because it's like these patches are quite small actually for optical astronomy. And that's why you can actually see like stars blink and other things like that, because actually the atmosphere is changing quite drastically. This is adaptive optics tries to account for this. And so, yeah, so we also need to make sure that's the case. So that's about 7-ish degrees.
2140 board.
Not much.
Do you know where the board might be? I know we're going to do a little white wire change to it. It's on the board itself right now. I can do it for him today. Otherwise, next week we'll be pretty busy.
Okay. So those are some of the main considerations that we want to take into account, as well as we want to make sure there's no other sources in these off beams. So we go through all the catalogs that exist in different radio regimes, and we make sure that there are no other sources that have been detected in those off beams. And we basically use gigahertz all the way down to like the LOFAR survey that's currently going on at the same wavelength as we do. So there's a variety of different things that play into that. So it is definitely a nice little balanced game that you have to do. And we put a lot of work into making sure that that's the case. And I've taken some like test observations to make sure there is no other things and them and stuff like that.
Is it signals before you make your observations?
Yes.
Slide?
So unfortunately, these are all queued observations. So in terms of like you actually programming the telescope while you're observing, you can't do that. So you have to do it in advance. So
I mean like the phasing, right? That's what you pick ahead of time and then the like correlator or whatever.
Right.
To make your team happen.
Exactly.
So that happens live. You can't like
Oh,
and then keep
right. So yeah, all that correlation is happening live. Yeah. And so one thing that we did, again, we talked about in our appendix was we noticed that there was some stations. So there's a lot of different stations, as you saw from LOFAR, that we eventually combined all that information together to get these beams. And we're assuming those are phased perfectly. You need a lot of work goes into that in terms of timing and other things. As we saw, they're not actually phased perfectly, which is a problem. But there were only certain stations that were causing that. But then because there's so much data that's being created at the telescope, once they phase all the observations together to get the dynamic spectrum that I showed you, they actually throw away each individual station observation. It would be great if they can keep that, but then they would have like so much data, it's not even funny. And LOFAR always has the largest, they like to say they have one of the largest databases of any entity in the whole world in terms of storage. So I don't know if that's true, but they're quite large. So they already have way too much data to handle as it is. And so just the consequence of like the correlator can only handle so much data, and also the actual like archive can only handle so much data. So you kind of lose some information, and we only know that because we have like diagnostic plots that are created, but they're like, you know, very coarse plots. And so that was something that we looked at, whether that was causing our possible signal detections. We don't think it was, but we did look into that. But it was like a lot more difficult than actually having that data. Thank you for those very good questions.
Like as a naive optical astronomer, like looking at the frequency plot of like your off-on beam, like by eye, they have a similar shape even if they have a different amplitude, and like that sort of like arouses my suspicion. Yeah,
so this is where another part of my extra slides, I think, comes into play. So this is, we went into this a lot in the paper. So this is actually, if you look at the actual raw on versus off, because of the imperfect phasing, we believe some of the on signal is actually being leaked into the off signal. So you can kind of see that right away by looking at that, but we actually proved that by looking at a pulsar. So every observation we take of an exoplanet, after and before that observation, we take 10 minutes of a pulsar, specifically for this reason I'm about to show. So we take, and it's the same exact setup as an exoplanet. So we take the pulsar observation, and we see that pulsar really good. We did an FFQ that's showing that. So we see the pulsar like super good, right? Because it's a really well-known studied pulsar, so it's to expect. And then we look for the pulsar in the off beams. And the pulsar actually shows up in both off beams as well. So we're actually seeing, because of this imperfect phasing, the leakage of the on-beam signal into the off-beam. So what you were seeing was actually that leakage itself, unfortunately. And we also did this with Jupiter as well, one of our Jupiter observations, which is here. So this is basically showing if you divide the on and off-beam, there actually is still some signal that's there as well. So yeah, unfortunately, this is one of the systematics that we do talk about in our paper that kind of made us weary that this might not be a real signal from space. And so this is why we really need multiple telescopes that observe at the same time. But thank you for that question. That is something that we definitely did think about a lot as well. And this is also interesting in terms of the systematics. So this is actually showing the two of the off beams for Tau Boo and the pulsar. And you can actually see, except for where we saw the emission from the exoplanet at, which we think is being leaked into the off beam, that all the other parts of the beam are exactly the same, right? So these are actually different parts of the sky, completely different parts of the sky. So you wouldn't naively be like, oh, these should be somewhat different, but they actually, some of these systematics are the same. So we actually think they're either coming from the instruments, not necessarily the sky. Anyway, that we also talk about that. But thank you for that question. Yeah, thank you for the wonderful detailed discussion. One more question.
How difficult is it to avoid Jupiter emission when doing observations?
Again, it's actually quite easy because people have been observing this for 26 years continuously, and we've observed it since the 50s. So you can actually predict when you expect Jupiter emission very, very precisely to the minute. And because one of the telescope that actually observed this is at one of the LOFAR sites, you can actually do these simultaneously as well. So if for whatever reason you have to have Jupiter above the horizon while you're observing, so you make sure it's not within the phase that you expect, but also you make sure you're observing it. So if you see an emission from a Jupiter that's different than what you predicted, because again, these are predictions, of course, then you can also account for that, right? So that's also a benefit. It's like Jupiter is being observed every night when it's up, all the time, every day, actually at the same site as Nenufar. So this is also a benefit.
And I know another discussion point that's useful bringing up, I know for especially a lot of APL staff, regarding the incorrect phasing leading to some erroneous results potentially. I know the way that radio astronomy and a lot of the radar background for a lot of the folks here, the way that we usually do it is we model what our synthesized beams are going to look like in terms of, for a theta and phi and azimuth and elevation, what kind of gain you're supposed to expect. And then you back out that response from that 3D pattern. And nothing of that source actually, or of that type currently exists for any data extraction for radio astronomy using low frequency beamformed observations. So if anybody's interested in that, that's definitely a way to make a dent in the field with some skills that I know some of the audience online especially have. All right, and any more questions? Any more questions online? Thank you everyone for coming virtually and in person. All right, with that being said, thank you for attending. Thank you, Jake, for the wonderful presentation. Thank you, everybody, for the detailed discussion. It was a pleasure, and yeah, thank you, and we'll look forward to doing it again sometime. Thank you, everybody, for attending.